There is a question physics has been circling for 100 years. Not the question of how stars form or why black holes exist. Those are interesting. This is different. This is the question underneath all the other questions. The one that, once you see it clearly, makes every other scientific problem feel like a distraction. The question is this: why does reality exist at all? Not how it began. Not what it is made of. Why it is here rather than not here. Why the rules that govern it exist rather than nothing existing at all. For most of human history, this question belonged to philosophers and theologians. Physics did not touch it. Physics measured things. Physics built equations. It left the deeper question alone, the way you leave a door alone when you suspect you will not like what is behind it. That changed. In the last 20 years, and accelerating sharply in the last decade, physics has produced a series of results that do not just approach this question. They answer parts of it. And the answers are not reassuring. They do not suggest that reality is solid, permanent, or necessary. They suggest the opposite. They suggest that reality is contingent, that it did not have to exist, that it does not have to continue, that the ground beneath every physical fact you have ever trusted is not a foundation. It is a temporary condition. This is not philosophy. These are measurements, equations, and experimental results. Numbers produced in laboratories and observatories around the world. The disturbing part is not what physics found at the beginning of reality. The disturbing part is what those findings imply about right now. About this moment. About whether the structure of everything you can see and touch and measure is as stable as it feels. It is not. To understand why, we have to start with the most recent number physics has produced. And that number came from the largest machine ever built by human hands. In July 2012, physicists at CERN announced the discovery of the Higgs Boson, the particle that gives matter its mass, the missing piece of the standard model of physics. It was a genuine triumph. Decades of work, billions of dollars, the largest scientific instrument ever constructed, all converging on a single number. And the number arrived. The number was 125.09 giga-electron volts. That is the mass of the Higgs boson. You might reasonably assume this is just a measurement, a data point to be recorded and moved past. But between 2012 and 2022, 4 independent research groups ran this number through the equations governing the electroweak field, the fundamental field that the Higgs boson maintains across all of space. What they found is that at 125 giga-electron volts, our vacuum sits in a state physicists call metastable. Metastable does not mean stable. It means stable for now, under current conditions, unless something disturbs it. Think of a glass balanced on the very edge of a table. It has been sitting there for 13.8 billion years. Nothing has knocked it off. You might look at that glass and conclude it is fine, that it will remain fine indefinitely. But the physics of the situation does not tell you the glass is safe. It tells you the glass has not fallen yet. Those are not the same statement. Our vacuum, the invisible substrate of space itself, the field that sets the rules for every particle and every force in the universe, is that glass. The electroweak calculations suggest it is not sitting in its lowest possible energy state. It is sitting in a local minimum. A shallow dip that feels like the bottom but is not the bottom. There is a lower state available, a true vacuum. And the difference between where we are and where the equations say we could be is the difference between the universe as it exists and the universe as it could not. Reality is not resting, it is holding its position. But what does metastable actually mean at the physical level? To understand that, we have to go one level deeper into what the vacuum actually is. The vacuum of space does not feel like anything. You cannot touch it, taste it, or measure it with your hands. It registers as absence, as nothing. But in quantum field theory, the vacuum is not nothing. It is a state, a specific energetic condition that permeates all of space at all times. It is the floor of reality. the baseline from which every particle, every force, every physical interaction is measured. And the floor, according to the calculations, is not the real floor. In 1980, physicists Sidney Coleman and Frank DeLucia worked out the mathematics of what happens when a vacuum is metastable. Their equations described a process called bubble nucleation. At any point in space, at any moment in time, quantum fluctuations can push a small region of the false vacuum over the energy barrier and into the true vacuum state. This creates a bubble, a sphere of true vacuum, expanding outward in all directions at the speed of light. Think of a container of supercooled water, water that has been cooled below freezing but has not yet turned to ice, because there is nothing for the ice crystals to form around. The water is metastable. It looks like water. It behaves like water. But introduce a single dust particle, a vibration, any small disturbance, and the entire container freezes in an instant. The phase transition is immediate and total. The bubble of true vacuum works the same way, except the container is the universe, and the phase transition does not produce ice. It produces a region of space where the physical constants are different, where the mass of the electron, the strength of electromagnetism, the rules governing atomic structure are all reset to different values. Values under which atoms as we know them cannot exist, under which chemistry cannot occur, under which nothing that currently exists can persist. The bubble expands at the speed of light. This is the detail that removes any possibility of response. Light is the fastest signal the universe permits. Information cannot travel faster than light. This means the image of the bubble's expanding wall, the light bouncing off the boundary between false and true vacuum, travels at exactly the same speed as the boundary itself. You would not see it coming. There is no version of events in which you see it coming. The wall of the bubble and the news of the wall arrive at the same moment. The last thing the universe would permit you to know is that this is happening. At the exact instant, it has already happened. Physics does not offer a detection mechanism. It offers only a description of disappearance. This brings us to the number that started the real panic in theoretical physics. A number that suggests the instability is not a minor technical problem, but something far more fundamental. Physics has a number it cannot explain. Not a number that is slightly off. Not a discrepancy that requires a small correction, but a number that is wrong by a factor that has no precedent in the history of science. A factor so large it suggests that something fundamental about our understanding of reality is missing. The number is 10 to the power of 120. Here is the problem. Quantum field theory. The most precisely tested scientific framework in human history, accurate to more decimal places than any other theory in any discipline, predicts a specific value for the energy density of empty space, the energy of the vacuum, the baseline energy that space itself carries even when stripped of all matter and radiation. The prediction is a large number, a very large number. Then physicists measured the actual energy density of the vacuum. They looked at the expansion rate of the universe, at the behavior of galaxies, at the geometry of space-time on the largest scales, and they got a number. The measured number is smaller than the predicted number by a factor of 10 to the power of 120. To understand what that means, consider this. There are approximately 10 to the power of 80 atoms in the observable universe. 10 to the 120 is not just larger than that. It is larger by 40 orders of magnitude. If you took the number of atoms in the observable universe and raised it to the power of 1.5, you would begin to approach the size of this discrepancy. This is not a rounding error. This is the largest disagreement between a theoretical prediction and an experimental measurement in the history of physics. It has been sitting in the equations, unresolved, for more than 60 years. Think of it this way. Imagine you are an engineer and you calculate that a bridge should weigh 120 tons. You then go and weigh the bridge. It weighs 1 gram. And the bridge is still standing. That is the vacuum energy problem. The calculation and the measurement are so far apart that the fact that anything exists at all requires an explanation that physics does not currently have. The standard model predicts a vacuum that should have torn reality apart before the first star formed. Something is wrong at the level of the foundations, and nobody in the field will tell you otherwise, however carefully they word it in public. Ask yourself, if the calculation is off by that much, and reality is still here, what exactly is holding it up? But perhaps the vacuum energy problem is not a flaw in the design. Perhaps it was set this way deliberately. Perhaps the numbers were always going to be exactly what they are. That is where the next layer begins. Let us be precise about what the physics actually says. Not what it implies, not what it suggests as a distant theoretical possibility, but what the equations of quantum field theory state as a direct consequence of the vacuum being metastable. The bubble of true vacuum, once formed, expands at the speed of light in all directions simultaneously. It is not a shock wave. It is not radiation. It is a boundary. A surface where the rules of physics on one side are different from the rules on the other, where the values of fundamental constants change discontinuously. Step across that boundary and you are in a region where the electron has a different mass, where electromagnetism operates under different parameters, where the nuclear forces that hold atoms together have different strengths. Everything built from the physics of the false vacuum, every atom, every molecule, every structure, ceases to be possible. Now consider the geometry of the problem. The bubble wall moves at the speed of light. Light from the bubble wall also moves at the speed of light. This means the light carrying information about the approaching wall and the wall itself travel toward you at the same velocity. They arrive together. There is no gap between the signal and the event. Think of standing in a field at night. In the distance, something is moving toward you in complete darkness. You cannot see it. You cannot hear it. The only way you would know it is there is if it emitted a flash of light the moment it reached you. That flash would be the first and last thing you perceived. The event and its announcement are simultaneous. There is no before. This is not a limitation of current technology. It is not a problem that better telescopes or faster computers will solve. It is a geometric consequence of the speed of light being both the speed of the threat and the speed of the information about the threat. No instrument, no matter how sensitive, can receive information faster than the information travels, and the information travels at the same speed as the wall. Physicists have searched for ways around this constraint. There are none. If the bubble forms close enough to reach us before the universe's expansion carries it away, we will not detect it in advance. We will not have time to record an anomaly. The last measurement our instruments make will be normal. The physics of our vacuum will appear stable and intact right up to the moment it is not. We are not looking for something we cannot find. We are looking for something that, by the structure of space-time, cannot be seen before it arrives. The silence of our instruments is not evidence of safety. It is what safety and destruction look like identical from this side of the wall. But perhaps the instability is not a flaw in the construction of reality. Perhaps the numbers were always going to be exactly what they are. Perhaps the constants that govern our vacuum were not accidental. That is where the next layer begins. And it is more disturbing than the one we just left. There are numbers written into the structure of reality. Not numbers that scientists invented to describe what they observed, but numbers that had to be exactly what they are for observation to be possible at all. Change them and the universe does not become different. It becomes nothing. Not a different kind of something. Nothing capable of structure, complexity, or time. The gravitational constant is one of these numbers. Gravity is the weakest of the four fundamental forces. Weaker than electromagnetism by a factor of 10 to the 36. Weaker than the strong nuclear force by a factor of 10 to the 38. It barely registers at the subatomic scale. You need masses the size of planets before it becomes the dominant force in the room. And yet, it is the force that shapes the universe on the largest scales. That pulls matter into stars. that collapses stars into the furnaces that forge the elements, that organizes those elements into galaxies, and the galaxies into the large-scale structure of everything we can observe. Now, consider what happens if you adjust the gravitational constant upward by 1 part in 10 to the 40th power. 1 part in 10,000 billion, 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 billion. A change so small, it has no analogy in ordinary experience, no object you could construct to demonstrate the difference. The universe collapses, not slowly, not after a long period of normal evolution, but in the first seconds after the Big Bang. Matter pulls together too fast. There is no time for stars to form, no time for nuclear fusion to begin, no time for the carbon and oxygen and nitrogen required for chemistry to be synthesized. The entire mass of the observable universe implodes before the first atomic nucleus stabilizes. Think of a dial. The dial goes from 0 to infinity. You're trying to hit a target zone that occupies 1 position out of 10 to the 40th possible positions. If the dial lands anywhere else, the game ends before it begins. Physics tells you the dial landed in the target zone. Physics does not tell you who set the dial or why the target zone exists. Now, adjust the gravitational constant downward by the same amount. The opposite failure. Matter disperses too quickly. Gravity cannot gather hydrogen into stars. The universe becomes a thin, cold, expanding fog. No fusion, no elements heavier than hydrogen, no planets, no chemistry, no time. The gravitational constant sits between these two failures, with a precision that has no explanation within the standard framework of physics. And gravity is only one dial. There are others, each one set with the same inexplicable precision, each one pointing at the same question that the gravitational constant raises and does not answer. This brings us to the question physicists spent decades trying to avoid asking out loud. In 1953, a British astrophysicist named Fred Hoyle did something that has no real parallel in the history of science. He predicted the existence of a physical property of the carbon atom. Not from an experiment, not from a measurement, not from a mathematical framework that required it. He predicted it from the fact that he was alive. The logic worked like this. Hoyle was studying stellar nucleosynthesis, the process by which stars forge elements heavier than hydrogen and helium through nuclear fusion. He knew that carbon is the backbone of all known chemistry. Every living cell, every protein, every strand of genetic material is built on carbon's ability to form stable bonds with other atoms. Without carbon, the specific kind of chemistry that produces self-replicating structures does not occur. He also knew how stars make carbon. In the core of a star, 3 helium nuclei must collide and fuse to produce a single carbon nucleus. This process, called the triple alpha reaction, requires something specific. The energy of 3 helium nuclei at stellar temperatures must closely match a resonance energy of the carbon nucleus itself. A kind of quantum tuning fork. If the energies align, the reaction proceeds efficiently. If they do not align, carbon does not form in meaningful quantities. Hoyle calculated what that resonance energy would have to be for carbon to form abundantly enough to produce a universe containing life. He got a number. Then he walked into a laboratory and told the experimentalists what to look for. They found it. Exactly where Hoyle said it would be. Think of what this means. Hoyle did not derive the resonance from first principles, he derived it from existence. He said, "We are here, carbon chemistry is the reason, therefore the carbon nucleus must have this property." He used the fact of his own presence in the universe as a measuring instrument, and the universe confirmed the measurement. The carbon resonance sits at 7.6567 mega electron volts. The resonance of oxygen, the next element up the chain, sits just low enough that carbon is not immediately converted to oxygen during stellar fusion. Both values are precisely positioned. If the carbon resonance were 4% lower, carbon would not form. If the oxygen resonance were 0.5% higher, all the carbon would convert to oxygen before it could be ejected into space. Both dials are set. Both are set to values that permit the specific chemistry required for the existence of the observer, asking why they are set that way. This is not a coincidence that can be dismissed. This is a second example of a constant sitting at a value that has no derivation from deeper physics, and no explanation from the standard model. It simply is what it has to be for the question to be asked at all. This brings us to the question physicists spent careers avoiding. If it is not a coincidence and it is not derivable, what is it? Einstein called it his greatest mistake. He introduced it to make his equations of general relativity produce a static universe, because in 1917, the idea of an expanding universe seemed physically unreasonable. When Edwin Hubble demonstrated in 1929 that the universe was expanding, Einstein removed the term from his equations and reportedly wished he had never added it. Then, in 1998, it came back. Two independent teams of astronomers, studying the brightness of distant supernovae to measure the expansion rate of the universe, found something their instruments should not have been capable of detecting. The expansion of the universe is not slowing down, it is accelerating. Something is pushing space apart, faster and faster, against the gravitational pull of all the matter in the observable universe. That something required a term in Einstein's equations. The cosmological constant, the energy of empty space, the same quantity Einstein had added and removed. Its observed value is approximately 1.1 times 10 to the negative 123rd power, measured in units of inverse meters squared. Now recall the vacuum energy problem from 2 steps ago. Quantum field theory predicts a value for this same energy that is 10 to the 120th power, larger than what we measure. But set that discrepancy aside for a moment, and look at the cosmological constant from a different direction. Ask what happens if you change it. If the cosmological constant was slightly larger, not by the factor of 10 to the 120th the quantum calculation is off by, but by a factor of just a few times its observed value, the repulsive force of the vacuum energy would have overwhelmed gravity in the early universe before matter could cluster into galaxies. Space would have expanded too fast. Matter would have dispersed into a cold, thin, structureless gas. No stars, no planets, no time for anything. If the cosmological constant were negative, if the vacuum energy were attractive rather than repulsive, the universe would have collapsed back on itself within the first billion years. A big crunch before the first generation of stars completed their lives. Think of a tightrope stretched across a canyon. The tightrope is one value wide. Everything to the left is one kind of catastrophe. Everything to the right is another. The cosmological constant is walking that tightrope. It has been walking it for 13.8 billion years. Physics does not explain how it found the tightrope. Physics does not explain why the tightrope is positioned where it is. The cosmological constant, the gravitational constant, the carbon resonance. 3 numbers. 3 dials set to values that permit structure. 3 dials whose settings are not derived from anything deeper in the current framework of physics. You might reasonably ask whether this is simply a failure of current physics. Whether a future theory will derive these values from first principles, and the mystery will dissolve. To understand why physicists stopped expecting that answer, we have to go to the landscape. For decades, physicists operated on an assumption so basic, it was rarely stated out loud. The assumption was this: the constants of nature have the values they have because a deeper theory will eventually derive them. The gravitational constant, the cosmological constant, the mass of the electron, all of these numbers feel arbitrary because we do not yet have the framework that makes them necessary. When we find that framework, the numbers will fall out of the equations the way the orbits of planets fall out of Newtonian gravity. They will stop being mysteries and become inevitabilities. String theory was supposed to be that framework. It replaced point particles with one-dimensional vibrating strings. It required extra dimensions of space beyond the 3 we experience. For 20 years, theoretical physicists invested enormous effort in developing it, because it seemed like the kind of deep structure that would finally explain why the constants are what they are. Then Leonard Susskind did the calculation. In 2003, Susskind worked out how many distinct vacuum states string theory actually predicts. Each vacuum state corresponds to a different way the extra dimensions of the theory can be curled up and configured. Each configuration produces a different set of physical constants, a different gravitational constant, a different cosmological constant, a different mass for the electron, a different universe with different rules, different chemistry, different everything. The number of distinct vacuum states is approximately 10 to the power of 500. Think about what that number means in practice. 10 to the 500 is not a large number the way a billion is a large number. It is a number of a categorically different kind. The total number of atoms in the observable universe is 10 to the 80. 10 to the 500 is larger than that by 420 orders of magnitude. It is a number so large that if you spent the age of the universe counting, you would not reach a fraction of a fraction of a fraction of it. String theory does not predict that our vacuum exists. String theory predicts that our vacuum is one entry in a catalog so vast that the word catalog loses its meaning. The theory does not tell you why the cosmological constant has the value it has. It tells you that somewhere in the landscape of 10 to the 500 possibilities, there is a vacuum with that value, along with vacuums where the cosmological constant is 1,000 times larger, and 1,000,000 times smaller, and every other value in between. This is not an explanation. This is the formal abandonment of the expectation of an explanation. A theory that predicts every possible universe predicts nothing about any specific universe. You have not explained the number. You have dissolved the question by making every answer equally valid. But what if there is no choice at all? What if the landscape is not a theoretical embarrassment but a physical reality? What if all 10 to the 500 vacuums actually exist? In 1986, the Russian-American cosmologist Andrei Linde published a paper that took the standard model of cosmic inflation and followed it to its logical conclusion. The conclusion was not comfortable. Inflation is the theory that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space expanded faster than light, doubling in size every tiny fraction of a second, stretching a region smaller than a proton into something larger than a galaxy in an interval too brief to measure by any ordinary standard. This expansion smoothed out the early universe, explaining why the cosmic microwave background radiation is so uniform, why the large-scale structure of the universe looks the way it does. The standard version of inflation ends. The exponential expansion eventually slows, the energy driving it converts into matter and radiation, and the universe settles into the more gradual expansion we observe today. Linde showed that in most versions of inflation, it does not end everywhere at once. In eternal inflation, the exponential expansion is driven by a quantum field. Quantum fields fluctuate. In some regions of space, the fluctuations cause the field to drop to a lower energy state, ending inflation locally and producing what looks from the inside like a Big Bang. A new region of space filled with matter and radiation, cooling and expanding, potentially forming galaxies and stars and chemistry. In other regions, the fluctuations push the field higher, keeping inflation going. Inflation does not stop. It keeps producing new regions, new pockets, each one a separate universe with its own physical constants, drawn from the landscape of possibilities that string theory describes. Think of it as a foam. Imagine an infinite foam of soap bubbles, each bubble forming inside an expanding medium that never stops producing new bubbles. Each bubble is a universe. Each universe has its own rules. Most bubbles are empty. Most bubbles collapse before anything interesting forms. A small fraction have constants in the right range for stars, and a smaller fraction still have constants in the range for chemistry, and a smaller fraction still have constants for biology. We live in one of the rare bubbles that permits the question to be asked. The implication is that the fine-tuning problem dissolves, not because someone set the dials, but because every dial setting exists somewhere. You observe a universe with life-permitting constants, not because those constants were chosen, but because only in universes with life-permitting constants can observers exist to notice them. This sounds like a solution. It is not. A theory that explains everything by positing that everything exists is a theory that explains nothing in particular. You cannot test it. You cannot falsify it. Even if every possible universe exists, you still have to explain why the laws that permit inflation exist, why quantum fields exist, why the mathematics of string theory applies to anything at all rather than nothing applying to nothing. You might argue this finally solves it. Infinite universes, infinite constants, we are simply the subset that can observe itself. It is not closed. It has been moved one level deeper, and the level below is darker than this one. There is an answer to the fine-tuning problem that is logically airtight. It requires no multiverse. It requires no deeper theory. It requires no mechanism at all. It simply points at a fact so obvious that it is almost impossible to see, the way you cannot see the air in a room until something moves through it. The answer is this: you are here. In 1974, the British physicist Brandon Carter formalized what he called the anthropic principle. The core of it is a single observation. The conditions you observe in the universe are not a random sample of all possible conditions. They are a sample filtered by the requirement that you exist to observe them. You cannot observe a universe that does not permit observers. Therefore, the universe you observe will always appear to have constants compatible with your existence, not because someone arranged them, not because they were selected from a landscape, simply because the alternative universes, if they exist, contain no one to notice that they exist. It sounds reassuring. It sounds like the mystery dissolves. Think of a man who survives a firing squad. 20 trained marksmen standing 10 meters away, all fire simultaneously. Every bullet misses. The man walks away. He might ask, what are the odds of that? He might feel that some extraordinary explanation is required. But there is a simpler observation available. If the firing squad had succeeded, he would not be asking the question. The fact that he is standing there asking is already proof that he survived. The question selects for the answer. The anthropic principle applies the same logic to the universe. The fact that you are asking why the constants permit life is already proof that you live in a universe where the constants permit life. No further explanation is required. This is where the logic becomes genuinely disturbing. Not because the anthropic principle is wrong. It is not wrong. It is impeccably correct. What is disturbing is what correct means here. Correct means that the constants of nature could be arbitrary, completely arbitrary. They do not have to have the values they have for any reason deeper than the fact that in universes where they have other values, no one asks. The universe does not have to be fine-tuned. It does not have to be designed. It only has to be the kind of universe in which the question can be formed. And that requirement, it turns out, is the only filter applied. You are not the product of a plan. You are the product of a filter. The filter is your own existence. The plan, if there was one, is indistinguishable from the absence of a plan observed from the inside. This is the most unsettling answer in science, not because it is incorrect, because it is correct and it says nothing. It tells you that reality did not have to be this way. It tells you that the apparent precision of the constants is a consequence of your position as an observer, not a feature of the universe itself. Reality is not fine-tuned for you. Reality is filtered by you. The difference is everything. This brings us to the question of what reality is actually made of at the level below the constants, below the fields and the particles and the forces. What physics found when it pushed past the numbers and into the structure underneath. Every physical process you have ever observed follows a rule, not a suggestion. A rule with no known exceptions, operating at every scale from subatomic to cosmological, for as long as physics has been able to measure anything. And nobody knows why the rule is the rule. Here is what it says. When a physical system moves from one state to another, it does not take a random path. It takes the specific path for which a mathematical quantity called the action is minimized. The action is computed from the energy and the geometry of the path. Among all the infinite paths a system could take, nature selects the one that makes this quantity an extremum. This should not work. There is no mechanism by which a particle, before moving, evaluates all possible trajectories and selects the optimal one. The particle has no information about the paths it did not take, and yet the path it takes is always the optimal one. Think of every physical process as a traveler who needs to get from one city to another. The traveler does not wander. The traveler takes the road that is optimal according to a specific mathematical criterion. Not a criterion the traveler chose, a criterion written into the structure of space and time itself. Every process in the universe, from the orbit of a galaxy to the decay of a single atom, obeys this criterion without exception and without awareness. Richard Feynman reformulated this in quantum mechanics and made it stranger rather than simpler. In Feynman's formulation, a quantum particle does not follow a single path. It follows all paths simultaneously. Every possible trajectory through space and time contributes to the particle's final behavior. The classical path, the one that minimizes the action, is simply the one where contributions from nearby paths add together constructively. The other paths cancel. What this means is that the principle of least action is not a rule imposed on nature from outside. It emerges from the quantum substrate as a statistical inevitability. The universe explores all possibilities. The minimum action path survives the interference. Everything else cancels. But this moves the mystery rather than dissolving it. Why do quantum amplitudes combine in exactly the way that produces least action behavior at larger scales? Physics states the rule with extraordinary precision. It does not state where the rule comes from. It has been sitting in the equations since the 1740s, unchanged and unexplained. The universe is not just following equations, it is following optimal equations. A universe that simply followed some equations would be unremarkable. A universe that follows the mathematically optimal path through every process at every scale is a universe that looks, from the outside, like a computation, which raises a question nobody in the field is comfortable with. If it is a computation, what is it running on? To understand how deep this structure goes, we have to look at what space itself is made of at the smallest scale physics can currently describe. The intuition about space is that it is continuous, that between any 2 points, no matter how close together, there is always another point. That you could zoom in forever and space would still be there, smooth and uninterrupted, an infinite substrate with no smallest unit. That intuition is almost certainly wrong. And the mathematics that says so has been sitting in peer-reviewed journals since the 1980s. Loop quantum gravity was developed over a decade by Roger Penrose, Lee Smolin, Carlo Rovelli, and collaborators. Its central claim is that space is quantized. It has a minimum unit of size below which the concept of distance loses its meaning entirely. That minimum unit is the Planck length, approximately 1.616 times 10 to the negative 35 meters. To give you a sense of scale, a proton is approximately 10 to the negative 15 meters across. The Planck length is 20 orders of magnitude smaller than a proton. If an atom were scaled up to the size of the observable universe, the Planck length would be approximately the size of a tree. Think of a photograph. Zoom in far enough and the continuous image resolves into individual pixels. Each pixel is either on or off, a discrete unit with no structure below its own scale. The image looks smooth from a distance because the pixels are small enough that your eye cannot resolve them individually. Space, in loop quantum gravity, has pixels. The pixels are Planck scale. The smoothness you experience is a low-resolution illusion generated by the fact that everything you have ever interacted with is enormously larger than the pixel size. At the Planck scale, space is not a smooth fabric. It is a network, a discrete web of nodes and links called a spin network. Each node represents a quantum of volume. Each link represents a quantum of area. The geometry of space emerges from this network, at larger scales, the way temperature emerges from the average motion of molecules. Temperature feels continuous. At the molecular level, it is discrete collisions. Space feels continuous. At the Planck level, it is discrete geometry. Now, what generates the spin network? What decides the geometry of the nodes and links? The spin network is not a static object. It evolves. It changes according to equations. But the network itself is not made of anything. It is not embedded in a background space. The spin network is space. There is nothing beneath it. If space is a network of discrete quanta, and if the network is all there is, then reality at its most fundamental accessible level is not made of stuff. It is made of connections between abstractions, not things in relationships, just the relationships themselves with no underlying substance that the relationships are relationships between. But if space is discrete, what about the rules that govern it? And here is where physics in 2024 runs into a wall it has not found a way around. Physics has two theories. Both are correct. They cannot both be correct at the same time. This is where the field has been for 100 years, and there is no sign of movement. General relativity describes gravity and the large-scale structure of the universe. Space-time curvature, black holes, the expansion of the cosmos, the bending of light around massive objects. Its predictions have been confirmed by GPS satellites, by gravitational wave detectors, by the photographed shadow of a black hole. It is a theory of smooth, continuous space-time geometry. Quantum field theory describes the other three fundamental forces and all known particles. Its predictions have been confirmed to more decimal places than any other theory in any scientific discipline. It is a theory of discrete, probabilistic quantum fields. When you try to combine them, when you try to write down an equation that describes gravity in quantum terms, the mathematics breaks. The equations produce infinities, not large numbers, actual infinities, values that diverge without limit and have no physical interpretation. The mathematics simply stops working. Think of two maps. One map covers everything west of a river. It is extraordinarily detailed, accurate to the millimeter, tested against every landmark. The other map covers everything east of the river with the same precision, but neither map includes the river itself. And the river is where the most interesting things happen. Black holes are the river. The Big Bang is the river. The Planck scale is the river. Physics has two perfect maps with a gap between them, and the gap is exactly where the origin of reality is located. String theory proposes one way to bridge the gap. It requires 10 or 11 dimensions of spacetime, it predicts 10 to the 500 vacuum states, and after 50 years of development, it has produced no unique experimental prediction that distinguishes it from competing theories or from no theory at all. Loop quantum gravity produces a discrete quantized spacetime and avoids the infinities, but it has not successfully incorporated the other three fundamental forces. It describes quantum space. It does not describe quantum matter in quantum space. As of 2024, no theory unifies general relativity and quantum mechanics. No theory describes what happens inside a black hole where both must apply. No theory explains the moment of the Big Bang where both are required and both break down. This incompleteness is not accidental. It may not be a temporary gap. It may be structural. And if it is structural, the question is not when physics will fill it. The question is whether the contents of the gap are even the kind of thing physics can describe. What is the map supposed to show when the territory is the absence of all maps? In 1931, a 25-year-old Austrian mathematician named Kurt Gödel published a proof that changed the foundations of mathematics permanently. Not a conjecture, not a hypothesis, a proof, a rigorous demonstration of something the mathematical community had assumed was impossible, and that, once demonstrated, could not be refuted. The proof said this: any formal mathematical system that is powerful enough to describe basic arithmetic contains true statements that cannot be proven within that system. Not statements that are difficult to prove, statements that are true genuinely and verifiably true, and that the system itself is constitutionally incapable of proving. The incompleteness is built into the structure of any sufficiently powerful formal system by mathematical necessity. To see why this matters for physics, you have to understand what a physical theory is. A physical theory is a formal system. It is a set of axioms, a set of rules for deriving consequences from those axioms, and a set of predictions about what will be observed. The standard model of particle physics is a formal system. General relativity is a formal system. Any theory of everything, any complete description of reality, would be a formal system. Gödel's theorem applies to formal systems. Think of a library that contains every book ever written, including books about the library itself. The library seems complete, but Godel showed that any sufficiently rich library of this kind must contain statements about itself that the library cannot verify. There are truths about the library that can only be seen from outside the library, from a position that, if the library is everything, does not exist. Apply this to physics. If the universe operates according to rules powerful enough to generate the complexity we observe, then by Gödel's theorem, there are true statements about the universe that cannot be proven from within it. There are facts about reality that are real, not arbitrary, but that cannot be derived from any theory constructed inside the reality they describe. This is not a statement about the limits of human intelligence. It is a mathematical theorem about the structural relationship between a system and its own description. No amount of progress in physics can produce a complete description of reality from inside reality. Sit with that for a moment. The full theory of everything cannot be found by anyone living inside the thing it describes. Not eventually. Not with better tools. Never. The incompleteness is not a gap we have not yet reached. It is the shape of the space we are standing in. The view from inside cannot see the outside. There is no outside available. But what if the problem is not the rules? What if the problem is the number of realities those rules permit? What if every time the rules are applied and a decision is required, every possible outcome happens simultaneously, and the universe we experience is only one thread in a structure of infinite branching? In 1957, a Princeton graduate student named Hugh Everett III submitted a doctoral thesis proposing a solution to the measurement problem in quantum mechanics. The solution was mathematically clean, logically consistent, and required no additional postulates beyond the standard equations of quantum theory. His thesis committee found it deeply uncomfortable. His advisor, John Wheeler, spent months trying to persuade him to soften the implications. Everett declined. The implications, he argued, followed directly from the mathematics. If the mathematics was correct, the implications were correct. The implications were these: the universe never makes a choice. Quantum mechanics describes physical systems using a wave function that encodes all possible states the particle could be in, with different probabilities attached to each. When you measure the particle, the standard interpretation says the wave function collapses. The superposition of all possible states resolves into one definite outcome. Everett asked a simple question: what collapses the wave function? What physical process causes a superposition to resolve into a single outcome? The standard interpretation gives no mechanism. It simply states that measurement causes collapse, without defining what a measurement is, without identifying the physical boundary between quantum systems and measuring devices. Everett's answer was that nothing collapses the wave function, because the wave function never collapses. What appears to be a collapse is actually a branching. When a quantum event occurs with two possible outcomes, the universe does not select one. Both outcomes happen. The universe splits into two branches, one containing each outcome. Both branches are equally real. Both contain observers who experience a definite result. From inside each branch, the measurement appears to have produced a single outcome. From outside the branching, both outcomes exist simultaneously. Think of a river reaching a fork. The water does not choose left or right. It goes both ways. The left branch and the right branch both exist. Both carry water, both continue downstream. An observer floating on a leaf in the left branch sees only the left branch. They conclude that the river chose left, but the river chose nothing. It simply flowed. Every quantum event is a fork. Every radioactive decay, every photon hitting a surface, every electron choosing a spin state. Right now, in this moment, there are versions of this conversation happening in branches where slightly different words were chosen. In branches where the reader stopped 3 paragraphs ago. The branching is not science fiction. It is what the mathematics of quantum mechanics predicts when you take it seriously. The disturbing part is not the existence of the branches. The disturbing part is what their existence implies about the branch you are in. You did not arrive here by selection. Every branch contains an observer who believes they are in the only branch. You are one of an uncountable number of instances of yourself, each equally convinced that their experience is the real one. The question is not whether this is true. The question is what selects the branch you experience. And the answer physics currently offers is nothing. The selection is an illusion generated by the structure of experience itself. The many worlds interpretation produces an immediate objection. If every quantum event splits the universe into branches, why do we never see the splitting? Why does the world around us look definite, classical, and singular? Why does a measuring device always show one number, not a superposition of all possible numbers simultaneously? The answer physics offers is called decoherence. It was developed systematically by the physicist Wojciech Zurek, beginning in the early 1980s. The mechanism is real, mathematically precise, and experimentally confirmed. And it solves exactly half the problem, which means it does not solve the problem. Here is what decoherence does. A quantum system in superposition interacts with its environment. The environment is vast. Billions of air molecules, photons, vibrations in the surrounding matter. Each interaction entangles the quantum system with one more degree of freedom in the environment. The superposition does not disappear. It spreads. It leaks out into the environment until it is distributed across so many particles that no practical measurement could ever detect the interference between branches. The superposition becomes, for all measurable purposes, invisible. Think of dropping a dye tablet into an ocean. The color does not disappear. It disperses so completely that no instrument you could build would detect it in any given sample. The dye is still there. You simply cannot find it. Decoherence explains why the classical world looks classical. It does not explain why you experience one outcome rather than another. It does not collapse the wave function. It hides the other branches. They are still there, fully real according to the mathematics, simply inaccessible from your branch because the information connecting you to them has dispersed irreversibly into the environment. This distinction matters more than it might appear. Decoherence is often presented as the solution to the measurement problem. It is not. It is a precise description of why the measurement problem is invisible in practice. The problem remains exactly wherever it left it. But decoherence does not solve the measurement problem. It hides it. The measurement problem is this. Quantum mechanics describes a physical system using a wave function that evolves smoothly and deterministically according to the Schrödinger equation. The wave function can exist in superposition, encoding multiple incompatible states simultaneously. But when you measure the system, you always get one definite outcome, never a superposition. One number, one position, one spin value. The problem is that the Schrödinger equation does not produce this. The equation never singles out one outcome. It evolves the superposition forward in time, spreading it, entangling it with the measuring device, entangling the device with the environment, but never collapsing anything into a single definite result. The mathematics says superposition. The experiment says single outcome. No one has written down a physical mechanism that bridges them. This is not a new problem. It was identified in the 1920s. Niels Bohr's Copenhagen interpretation handled it by simply declaring that measurement causes collapse, without specifying what measurement is or what collapse means physically. That declaration has been the working assumption of most physicists for 100 years, not because it is satisfying, but because it produces correct predictions and allows you to continue doing physics without confronting the gap. The gap is still there. As of 2024, there is no consensus interpretation of quantum mechanics. There is Copenhagen, which avoids the problem by refusing to describe what happens during measurement. There is many worlds, which eliminates collapse by multiplying universes. There is pilot wave theory, which adds hidden variables. There is QBism, which relocates the problem into the mind of the observer. Each interpretation is mathematically consistent with all known experimental results. Each gives a different answer to the question of what is actually happening when a quantum system is measured. Physics cannot tell you which one is correct. The experiments that would distinguish them are not currently possible. The most precisely tested theory in human history does not know what it is describing. This leads to a thought experiment that makes the measurement problem impossible to ignore. In 1998, the physicist Max Tegmark published a paper examining a logical consequence of the many worlds interpretation that most physicists preferred not to discuss. He called it quantum suicide. The argument is simple, the conclusion is not. Imagine a device connected to a quantum random number generator. The generator has a 50% probability of outputting 0 and a 50% probability of outputting 1. If it outputs 0, the device does nothing. If it outputs 1, the device terminates the person operating it, instantaneously and without warning. You sit down at the device and press the button. In the many worlds interpretation, the universe splits into two branches. In one branch, the number is 0, you survive, and you hear a click. In the other branch, the number is 1, and the device activates. From the outside, an observer watching you has a 50% chance of seeing you survive each trial. Run the experiment enough times, and the outside observer will almost certainly watch you die. But from your own perspective, the story is different. In every branch where you die, there is no perspective to be had. Dead observers do not experience anything. The only branches you can ever experience are the branches in which you survived. No matter how many times the experiment runs, no matter how improbable your continued survival becomes from the outside view, from your own first-person perspective, you will always find yourself in a branch where the number came up 0. Tegmark argued this implies a form of quantum immortality. Not that you cannot die. You die in most branches. But the branches where you die contain no experience of dying. Your subjective experience always continues in some branch, however improbable that branch becomes. This is not a statement about biology. It is a statement about the structure of observation in a branching universe. Death is not the end of experience. It is the end of experience in branches you can no longer access. Before we go further into the observer, we need to question the ground they stand on. We need to ask whether the time in which observers exist is what it appears to be. In 1967, John Wheeler and Bryce-DeWitt attempted to apply quantum mechanics to the universe as a whole, not to a particle inside the universe, not to a field propagating through space-time, to the entire universe, treated as a single quantum system described by a single wave function. The equation they produced is called the Wheeler-DeWitt equation. It describes the quantum state of the universe. It is the closest thing physics has to a wave function of everything. The equation has no time variable, not a hidden time variable, not an implicit time variable that can be extracted through a change of coordinates, no time variable at all. Time, the dimension you experience as the medium through which events unfold, the parameter that appears in every other equation in physics as the independent variable against which everything else is measured, is absent from the fundamental equation governing the quantum state of the universe. You might argue this is a technical artifact, a sign that the equation is incomplete, waiting for refinement. That is a reasonable position to hold. It is also the position physicists have held for 50 years while the time variable remains absent. At some point, the absence is the data. This is a consequence of the structure of general relativity combined with quantum mechanics. General relativity treats time as a dimension of space-time, not as an external parameter. When you quantize gravity, time gets absorbed into the geometry of the system. It becomes a degree of freedom of the universe itself, rather than the background against which the universe evolves. The result is an equation that describes all possible states of the universe simultaneously, with no preferred sequence, no before, no after. Think of a photograph. A photograph does not show movement. It shows all the information of a moment frozen into a static object. The Wheeler-DeWitt equation describes the universe the way a photograph describes a face. Every configuration the universe has ever been in, or ever will be in, is encoded in the wave function simultaneously. The sequence you experience as time is not written into the fundamental description. If time is not fundamental, what is it? Einstein's special theory of relativity, published in 1905, produced a consequence that its author understood clearly, and that most people have not fully absorbed in the centuries since. The consequence is that there is no universal present moment. There is no single instant that is now for the entire universe, simultaneously. In Newtonian physics, time is absolute. The present is the same for everyone. Two observers, no matter where they are or how fast they are moving, share the same now. Events happen in a definite sequence. Before and after are objective facts about the universe. Relativity eliminated this. Two observers moving at different velocities disagree about whether two distant events are simultaneous. There is no fact of the matter about which one is right. Simultaneity is not a property of events. It is a property of reference frames, and reference frames are relative. Hermann Minkowski, Einstein's former mathematics teacher, drew the correct conclusion in 1908. If simultaneity is relative, then the distinction between past, present, and future is also relative. The only objective structure is four-dimensional spacetime, where all events, past, present, and future, exist as points in a four-dimensional geometry. No point in this geometry is privileged as the present. This is the block universe. The idea that all moments of time exist with equal reality, the way all points in space exist simultaneously. Your birth and your death are both there, fixed points in the four-dimensional geometry, as real as the moment you are reading this. The experience of time passing, of the present moving from past toward future, is not a feature of the universe. It is a feature of consciousness moving through a static structure. Think of a novel. Every page of the novel exists simultaneously in the physical book. The characters experience events sequentially. But the sequence is in the reading, not in the object. The block universe suggests that what we call time is the reading, not the book. But if all moments exist, why do we experience them in only one direction? Physics is almost entirely symmetric in time. Take any equation describing a fundamental physical process and run it backwards. The reverse process is equally valid, equally permitted by the laws of physics. A film of two billiard balls colliding looks physically plausible whether you run it forward or backward. At the level of fundamental physics, both directions are the same. And yet time has a direction. You remember the past and not the future. Heat flows from hot to cold and not the reverse. Eggs break. They do not reassemble. Something breaks the symmetry. That something is not a law. It is a count. Entropy is a measure of disorder, of the number of microscopic arrangements that produce a given macroscopic state. A broken egg has higher entropy than an intact one because there are vastly more ways to arrange molecules into a broken configuration than an intact one. The second law of thermodynamics states that entropy tends to increase not because nature prefers disorder as a matter of principle, but because disordered states vastly outnumber ordered states. If you scramble the system randomly, it almost certainly ends up in a high entropy configuration. Not by law, by the weight of numbers. This is the arrow of time. The thing that makes the past feel like the past and the future feel open is not written into the fundamental structure of the universe. It emerges from the initial conditions. Specifically, from the fact that the early universe was in an extraordinarily low entropy state, smooth and uniform, and improbably ordered. Everything since has been the long statistical slide toward equilibrium. Think of a room where someone spent 3 hours arranging grains of sand into a perfect pattern. You walk in, sneeze, and the pattern is gone. The sneeze did not destroy it according to some law against beautiful sand patterns. The sneeze simply introduced random motion, and random motion overwhelmingly favors the vastly more numerous disordered configurations. The pattern was the anomaly. The mess is the default. Our universe started as the pattern. It has been becoming the mess ever since. The direction of time is not a feature of physics. It is a memory of a starting condition we cannot explain. Why the early universe was in that extraordinarily ordered state is a question the second law cannot answer. The arrow points forward because we started somewhere very special. Where that starting point came from is the question underneath everything else, and it will still be waiting when we get to the end. This brings us to the smallest unit of time physics can currently describe. The Planck time is 5.39 times 10 to the negative 44 seconds. It is the scale at which all current physical theories break down. Below this scale, the concept of time may not apply. Not because our instruments are too crude, because the equations cease to produce meaningful results at that resolution. Carlo Rovelli has argued that time at the Planck scale is not a continuous flow, but a discrete sequence of quantum transitions. Between transitions, there is no time. Not slow time, not frozen time, no time at all. Think of a film projected at 24 frames per second. Between frames, the screen is dark. The story exists only in the frames. Slow the projector below a certain threshold, and the darkness becomes visible. The continuity breaks. You see what the illusion is made of. Planck time is the frame rate of reality. The universe is reconstructed at 10 to the 43 times per second. At the fundamental level, there are only frames. Between frames, nothing is there. What does the reconstructing is the question that sits beneath all the others. To understand that, we have to ask what reality is made of at a level below space and time. Between Planck frames, nothing holds space together. What does the holding? John Wheeler spent 60 years at the center of theoretical physics. In 1989, he arrived at a conclusion he had been approaching for decades. He called it from bit. Every physical quantity is ultimately registered as a yes or no answer to a binary question. A particle is detected or not detected. A spin returns up or down. At the level of fundamental physical interaction, the universe communicates in bits. Wheeler's claim, information is ontologically prior to matter. The particle is what you get when the universe answers a binary question. Matter is crystallized information. Space is the geometry of informational relationships. Think of a conversation. Two people exchanging questions and answers. The conversation is not made of air molecules, even though air molecules carry the sound. The conversation is made of meaning. Wheeler argued that the universe is more like a conversation than like a machine. The information is the message, and the message is what is real. If reality is made of information, the question of its origin changes shape entirely. The question is not what physical object existed first. The question is, what question was asked first? If reality is information, then it has a surface. In the early 1990s, Gerard 't Hooft and Leonard Susskind proposed the Holographic Principle. All the information required to describe the physics of a three-dimensional region of space is completely encoded in the two-dimensional boundary surface surrounding that region. The principle emerged from black holes. Hawking showed that a black hole's entropy scales with the area of its event horizon, not its volume. The information is on the boundary, not inside. 't Hooft and Susskind generalized this to all of space, 1 bit per Planck area. Think of a snow globe. Everything inside appears three-dimensional. But if the holographic principle applies, all of that information is encoded on the glass surface. The interior is a projection. The reality is the surface. The three-dimensional space you move through may be a projection of a two-dimensional informational structure. not a simulation in the science fiction sense. A mathematical fact about how information is stored in the geometry of space-time. But information has a physical cost, and the cost tells us something about why reality exists at all. In 1961, Rolf Landauer, a physicist at IBM, proved that information is physical. The act of erasing one bit of information has a minimum thermodynamic cost that cannot be reduced regardless of how efficient your technology becomes. When you erase a bit, you reset a two-state system to a known state. This is irreversible. By the second law, reducing possible states requires increasing the entropy of the surrounding environment. The minimum energy per erased bit is kT times the natural logarithm of 2. The cost cannot be zero. Thinking has a thermodynamic price. Think of thought as burning fuel. Every time a bit is erased and reset, heat is released. Not as a consequence of inefficiency, as a consequence of physics. A perfect lossless computer still generates heat when it erases information. The universe has been processing information since the Big Bang. Every quantum interaction is a computation paying the thermodynamic price of its own operation since the first Planck interval. Information is not a description of reality. Information is what reality is made of, and reality has been spending itself to think since the beginning. This brings us to the most disturbing connection physics has made in the last decade. In 2013, Maldacena and Susskind published ER equals EPR. Wormholes are mathematically identical to quantum entanglement. Entanglement is geometry. The fabric of space is woven from entanglement. Remove the entanglement and the space between regions does not become large. It ceases to exist. Think of a net. Cut the strings and the knots stop being a net. Space is that net. Entanglement is the strings. Space is not the container in which physics happens. Space is a consequence of informational relationships between quantum systems. And if you could sever the entanglement, the space would dissolve. Reality is not stable because space is solid. Reality holds its shape because the information connections are intact. The structure is not a fact. It is an ongoing process. But who reads that information? The double-slit experiment has been performed thousands of times. The result is always the same. It has never been explained. A source fires particles one at a time at a barrier with two narrow slits. When no detector is placed at the slits, you get an interference pattern. The particle passes through both slits simultaneously, interferes with itself, and lands where the interference dictates. A single particle, two slits, both paths at once. Place a detector at the slits. The interference pattern disappears. The particle behaves like a bullet. Modern detectors can interact with the particle at the theoretical minimum of disturbance. The interference pattern still disappears the moment the witch path information becomes available, in principle anywhere in the universe. The presence of information about the path, not physical disturbance of the particle, determines the outcome. Reality arranges itself differently depending on whether it is observed. Where the witch path information exists, in a form that could in principle be recovered, the interference vanishes. Where it does not exist, the interference appears. The universe responds to the informational structure of the situation, not just the physical one, but it gets stranger than that. In 1978, John Wheeler proposed an experiment. In 2007, Alain Aspect's team in France confirmed Wheeler's prediction exactly. The decision about whether to measure which path the particle took is made after the particle has already passed through the slits. The particle has, by any ordinary understanding of physics, already completed the part of its journey where it either went through one slit or both. Then, retroactively, the experimenter decides whether to extract the witch path information. When the experimenter chooses to extract the information, the interference pattern is absent. When the experimenter chooses not to, the interference pattern is present. The particle's behavior at the slits, the event that has already happened, is determined by a decision made after it happened. The past state of the particle is not determined until a measurement is made in the present. The history is not written until someone decides to read it. Wheeler described the universe as participatory in a precise physical sense. Observations made now contribute to the definition of what happened then. The past is not a fixed record that the present reads. The past is a structure that the present helps to constitute. This has led some physicists to a radical conclusion about what quantum mechanics is actually describing. QBism, pronounced QBism, stands for quantum Bayesianism. Foundational paper, Fuchs, Schack and Mermin, 2001. The central claim: the wave function is not a description of an objective physical reality. It is a description of the beliefs and expectations of a particular agent about their future interactions with the world. Think of a weather forecast. It is not the weather. It is a description of what a specific forecaster expects the weather to do. In QBism, every quantum measurement is structurally identical to this. The wave function collapse is something that happens to the observer's expectations, not to the particle. This dissolves the measurement problem completely. Quantum mechanics is not a description of what happens. It is a tool that agents use to navigate their experiences. You might argue, physics must describe something objective. That is a reasonable position. It is also the position physicists held for 100 years, while the measurement problem remained unsolved. Here is what this implies. Physics does not describe an observer-independent reality. It describes the relationship between observers and their experiences. The territory may not exist independently of the mapping, but if reality is relative to the observer, whose reality is the real one? Carlo Rovelli published his relational interpretation in 1996. It dissolves the measurement problem without involving mental states. It makes the theory about physical relationships between systems, regardless of whether they are conscious. Physical properties do not exist absolutely. They exist only relative to other systems. An electron does not have a definite position. It has a definite position relative to this detector, and no position at all considered in isolation from any detector. Think of price. An object does not have a price in isolation. It has a price relative to a buyer, a market, a moment in time. Rovelli argues all physical properties are like price, relational, not intrinsic. The universe is not a collection of objects with properties. It is a network of interactions, each one constituting local facts relative to the interacting systems, with no global view available from outside. Reality is not one thing seen from many angles. It is many things, each real relative to its local context, with no master version. But what if all these realities are equally real in a deeper sense? What if mathematics itself is the universe? A complete description of reality would have to be expressible in a language any intelligence could derive independently. The only such language is mathematics. Max Tegmark took this one step further in a 2007 paper. If the description is mathematical, and if mathematical structures exist independently of physical instantiation, then the description is not a map of the territory. The description is the territory. The mathematical structure does not represent the universe. It is the universe. Think of a novel. The characters are real within the novel. They have consistent properties, histories, relationships. Tegmark's claim is that our universe is in the same position relative to the mathematical structure that describes it. We are inside the equation, not described by it, made of it. This means the question of why our universe exists becomes, why would this particular mathematical structure not exist? If mathematical structures are real in the strongest possible sense, the default is existence. You do not need to explain why something exists. You need to explain why anything would not. This is not philosophy. This is a falsifiable scientific claim. The same theorems hold in ancient Greece and 21st century laboratories. The same prime numbers appear in the same positions. Nobody put them there. They were discovered, not invented. They were waiting before any human mind existed to find them. Tegmark calls this the external reality principle. Follow it carefully, and it eliminates every human element from the description of reality, until what remains is the abstract structure of the relationships themselves. The pattern without the symbols. The logic without the words. Think of a piece of music. Strip away the performance, the instruments, the notation. What remains is the mathematical structure of the relationships between the notes. Tegmark argues the universe, stripped of its physical trappings, is like that music. The physical stuff is the performance. The mathematics is the piece itself. If mathematical structures exist necessarily, without requiring a cause, then the question of why our universe exists dissolves into, why would any mathematical structure fail to exist? The default is existence. Non-existence would require explanation. And if it is a mathematical structure, it can be computed, which raises a question harder to dismiss than it appears. In 2002, Stephen Wolfram published a 1,200-page book with a central claim: simple computational rules, applied repeatedly, can generate all the complexity observed in the physical universe. Wolfram had spent years studying cellular automata, grids of cells updating according to a simple rule. Rule 110, one of the simplest, has been proven computationally universal. Any physical process that can be described mathematically can be reproduced by some cellular automaton. Wolfram's argument, the universe itself is a cellular automaton. Fundamental entities are nodes in a computational network, updating at each Planck time step. Space and time and matter and energy emerge from the computation. They are not inputs, they are outputs. If reality is computable, computable things can be run. Pause on that. A computable universe is a universe that could, in principle, be instantiated by anything capable of executing the rules. It requires only that the computation runs, which means the question of where the rules came from becomes unavoidable. Before we go there, we need to ask whether the process had a beginning at all. In 1983, Stephen Hawking and James Hartley proposed the no-boundary condition for the universe. Their answer to the question of what caused the initial state. The question is malformed. Near the Big Bang, where quantum effects dominate, the time dimension can undergo a mathematical transformation that makes it behave like a spatial dimension. In a region of space-time where time is space-like, there is no beginning. Ask what happened before the South Pole, and the question reveals its own incoherence. There is no south of the South Pole. In the Hawking-Hartley model, asking what happened before the Big Bang is equally incoherent. Time as a direction simply does not extend to the other side. There is no other side. The universe did not begin. It has no boundary in time. The requirement for a cause only applies to events within time. The universe is not within time. It is what time is inside of. But what if the Big Bang was not a boundary at all? What if it was a transition? Neil Turok, Paul Steinhardt, Justin Curry, and Bert Overoot developed the ekpyrotic model in 2001. The name comes from the Greek word for conflagration. In this model, the Big Bang was not the beginning of the universe. It was a collision. String theory predicts that our three-dimensional universe is a membrane embedded in a higher dimensional space. Multiple membranes can exist, parallel to each other, invisible to us. In the ekpyrotic scenario, our universe and a neighboring membrane slowly drifted toward each other. When they collided, the energy was deposited as heat and matter uniformly across both membranes. From our perspective, this looks exactly like the Big Bang. But the membranes existed before the contact, and will exist after. Our Big Bang is not a unique event in an otherwise empty eternity. It is one episode in an ongoing process. The model predicts a cyclic cosmology. After the collision, the membranes bounce apart, cool, empty out, and begin approaching each other again. We are living inside one echo in an infinite sequence of collisions. Roger Penrose proposed his conformal cyclic cosmology in 2010. It begins from an agreed-upon observation. The universe began in an extraordinarily low entropy state, and will end in an extraordinarily high entropy state. The heat death. A featureless expanse where no thermodynamic process is possible. Penrose noticed both extremes share a mathematical property called conformal flatness. His proposal, the remote future of one universe can be matched to the Big Bang of the next. the heat death does not end in nothing. The geometry of maximum entropy is indistinguishable from a new low entropy beginning. In 2010, Penrose and Vahegozadian reported anomalous circular patterns in the cosmic microwave background, possible imprints from the previous eon. A 2011 analysis by the Hajian group did not confirm the signal. The debate continues. But all of these models share one assumption none of them can justify from within their own frameworks. Every cosmological model has a flaw, conditions it must assume rather than derive. None of these models explains why the laws they assume exist. Physics names the bottom of the chain initial conditions, specific values of energy, entropy, and geometry that it takes as given without explaining why those values and not others. Think of a calculator. You enter a number and it produces a result. The calculator cannot tell you where the number came from. The universe is the calculator. The initial conditions are the numbers someone typed in. No one knows whose fingers did the typing. Every theory must assume something. A theory that explained its axioms from deeper axioms merely relocates the problem. The regress is not a failure of physics. It is the structural shape of explanation itself. We have reached the wall, not the edge of current knowledge, a boundary where the tools of explanation run out not because they are blunt, but because sharpening them does not help. This is where physics stops, and philosophy begins, but philosophy does not let you off easy either. In 1714, Gottfried Wilhelm Leibniz posed a question in a single sentence that has not been answered in the 312 years since. Why is there something rather than nothing? Not how did the something begin? Not what rules govern it? Why does existence exist rather than non-existence existing instead? Every physical theory begins with existence. Quantum field theory assumes fields. General relativity assumes space-time. String theory assumes strings. None of them explain why there is something for the laws to govern rather than nothing. This is not a gap at the edge of physics. It is a gap beneath physics. There are only 3 honest answers to this question, and all 3 of them are disturbing. The first answer is necessity. Reality exists because it could not fail to exist. Existence is logically necessary. Nothingness is not a coherent alternative. But this requires identifying what feature of reality makes it necessary, and every attempt either assumes something that exists, which is circular, or identifies a logical structure that must exist necessarily, which relocates the question one level deeper. The second answer is contingency. Reality exists for no reason at all. The universe is a brute fact, logically consistent, cannot be refuted. But it violates the principle of sufficient reason, the intuition that every fact has an explanation. If reality is a brute fact, everything we think of as understanding is just the internal structure of a contingency we can never justify. The third answer is that the question is malformed. Ludwig Wittgenstein argued in the Tractatus Logico-Philosophicus, published in 1921, that some questions arise from misuse of language. Why is there something rather than nothing presupposes a perspective outside existence from which non-existence could be observed. A perspective that does not and cannot exist. The asking is itself an act of existence. The question destroys itself. All 3 terminate something you did not want to terminate. Necessity by assertion. Contingency by abandonment. Wittgenstein by dissolution. There is one final implication that physicists rarely discuss openly. Return to the beginning. Not to the Big Bang. To the experiment with 2 slits. The particle exists in superposition until it is observed. The delayed choice experiment shows the past state of the particle is not determined until a measurement is made in the present. In QBism, the wave function has no value independent of an observer's experience. These are the central results of the most precisely tested theory in physics, and they converge on something rarely stated plainly. The classical, definite, structured reality you experience is not the default state of the universe. It is a state constituted, moment by moment, by the ongoing process of observation and interaction. What emerges as definite, located, structured reality does so through the act of physical interaction. Remove all observers. Remove all physical systems capable of registering information. What remains is a quantum superposition of all possible configurations with no definite values. Not nothing, but nothing structured, nothing definite. Frank Tipler, in his 1994 book, The Physics of Immortality, took this to its furthest point. The equations do not require that observers continue. If they stop, the process that generates definite reality from quantum possibility stops with them. Think of a standing wave in water. It has location, frequency, shape, but stop the water and the wave ceases to be a wave. Reality may be more like that wave than like a rock. A pattern maintained by the ongoing process of interaction. The universe did not have to exist. It does not have to be stable. It does not have to continue. The reason it currently has the specific character it has, definite, located, structured, is that it contains systems that interact with it, and in interacting with it, constitute it. We are not watching reality. We are part of what is holding it together. That is not a comfortable conclusion. It never was.